Okay, so we are 10 after the hour. Welcome to everyone to this week's CDAR seminar. I'm Lisa Goldberg, CDAR's co-director, and it is my great pleasure to introduce Priya Donti, a professor at MIT, who's going to talk to us about a subject close to all of our hearts, optimization in the loop machine learning for energy and climate. So Priya, over to you.
Awesome. Well, yeah, thanks so much, Lisa, and to Wooter and to Sang and to everybody who kind of organized this. I'm really excited to talk about this with you. Yeah, so diving right in. So the work that I do is as I think is shared within this group, very motivated by addressing problems of climate change. So climate change is, of course, one of the most pressing challenges that we as a society are facing today, with its impacts felt globally and disproportionately by the world's most disadvantaged populations. And in order to hit, targets from, for example, the UN Intergovernmental Panel on Climate Change to hit net zero greenhouse gas emissions by 2050, we as a society are going to need to transform virtually every sector of society across energy, transport, buildings, agriculture, and so forth. And so for someone like me coming from a machine learning background, then maybe a natural question to ask is, given that we need kind of all hands on deck, all tools on deck with addressing climate action, is machine learning one of those tools that can potentially play a role in helping us to actually do that? And, several years ago, a group of collaborators and I came together to actually explore this question more systematically. Where is it that machine learning can potentially play a role in climate action? And we put out this paper, Tackling Climate Change with Machine Learning, which, over a short 100 pages or so, outlined some applications across many different sectors, ranging from helping us to more effectively integrate renewables into power grids, to helping us optimize heating and cooling systems in buildings more efficiently, to predicting the carbon content in soil in order to foster better agricultural practices that actually increase carbon sequestration potential. So across these applications, we saw a lot of places where machine learning could already today play a role. That said, we also saw some gaps, places where, because machine learning has honestly primarily been developed with certain kinds of domains and certain kinds of data in mind, for example, text and image data on the internet, where today's machine learning methods didn't necessarily always fully meet the on-the-ground requirements of some of the climate change related areas that we really wanted to help address. And so my work dives into one specific example of that in order to try to enable machine learning to be used in certain additional climate relevant sectors. And specifically, a lot of my work thinks about the power and energy system. So when I talk about power systems, I'm talking about the system through which our electricity is produced, then transported along lines and electrical equipment, and then eventually consumed by end-use consumers like us. Power systems make up about a quarter of global greenhouse gas emissions, and they're also especially essential to decarbonizing sectors like buildings, transportation, that basically rely on electrifying various loads within those sectors and kind of plugging them into a clean grid. So, of course, there have been a lot of initiatives to think about how do we actually clean up the power grid. But making large-scale changes to the power grid is difficult because fundamentally they are physical and safety-critical systems. When you put power into the grid, it flows along the lines and electrical equipment based on physical laws. There are various hard constraints one needs to think about, like ensuring that you're not asking your power generators to generate an amount of power they can't actually generate, or to change their power output in a way that they can't actually do. And you also need to make sure the grid stays near some kind of electrical equilibrium, that it's maintaining some stability constraints. And layered on top of all of that are various decision-making procedures that are happening at timescales ranging from the sub-second level to the years ahead level, where we're trying to solve problems like, given uncertain electricity demand, how do we schedule supply subject to all these constraints to minimize costs? Or how do we actually plan our power system? How do we actually build things out such that we know we can balance our system in the future? So making large scale changes on power grids is difficult because you have to contend with all of these physics, hard constraints, and decision-making procedures. Now, the challenge is that we do have methods today that can deal with these physics hard constraints decision-making procedures to an extent, and these are traditional methods from optimization and control. But what we're starting to see is that as we introduce more, for example, renewable energy onto the power grid, where the output of that energy varies from moment to moment based on the weather, and you also have larger scales at which you need to manage your power grid, because now we have more power generators, batteries, electric vehicles, distributed devices that we have to optimize. The speed and scale of this problem is rapidly increasing and is sort of outpacing the ability of optimization and control methods to canonically handle. And so machine learning has been proposed as a potential set of methods that can address this, because machine learning methods are good at the speed and scale aspect. So for example, one thing that's needed on the power grid is to adaptively control power generators, inverters, and batteries on the system in a way that kind of improves performance but maintains some of the physical needs of the system. And machine learning is really good at the dynamic and data-driven part of coming up with scalable and fast and well-performing controllers. But what it's bad at is enforcing the physical constraints, like the physics and equipment constraints that are necessary to support on the grid. If you don't do this, you might black out your power system. And of course, you really don't want to do that. We also have needs for things like, prediction and foresight on the power grid, so predicting electricity demand. And machine learning has been, proposed as a solution for, okay, we can ingest all sorts of data and provide better time series forecasts on the power grid. But even here, machine learning methods are limited in the sense that they traditionally are often optimizing when they're making a forecast for something different than what we actually care about on the system. When we make a forecast, we use that forecast to make some kind of decision. And what we ultimately care about is the quality of the decision-making process, not necessarily the raw forecast itself. So machine learning methods have some difficulty making these kinds of, decision cognizant error trade-offs. So the question that my work asks then is, how do we reap the benefits of machine learning methods, this dynamic and data-driven control, this ability to do powerful time series forecasting, while mitigating its limitations in dealing with physics, hard constraints, and decision-making processes? And so to do this, my work proposes a paradigm called optimization in the loop machine learning that aims to combine our knowledge of physics, hard constraints, and decision-making processes into machine learning methods. So the way we do this is by basically saying there are a lot of, again, physics, hard constraints, and decision-making procedures that we can characterize as optimization problems. And if we can formulate the right optimization problems, we can maybe embed those into our machine learning models or into the objective functions that our machine learning models use to learn. And by doing that, we can ideally create these machine learning methods that can learn from data, that can learn to be scalable and dynamic and responsive to what's going on a system, but also inherently, because of how they're designed, know how to satisfy physics constraints and decision-making procedures. And so to give some examples of how this might play out, I want to go back to the two motivating examples I used earlier in this talk about control and forecasting in power grids. So in doing this, I'm going to use this pictorial representation of a machine learning model where X represents the inputs to the model, H is the functional form of the model, theta are its adjustable parameters, and H sub theta of X are then the outputs of our model. So the first example I gave earlier of a setting where we would want to use machine learning, but it's not already fully there, is adaptive and robust control of components on power grid. So for example, we're trying to control an inverter on a power grid, but we want to do this in a way that maintains stability constraints. So this might be a setting where we have the reinforcement learning setting, where we have a model that takes in some information about the state of our underlying system and output some control action. And the hope is that we can embed some knowledge within the machine learning model to make sure that the control action it's outputting is actually robust. The other example I gave earlier is prediction, where we want to create a forecasting model for things like electricity demand in a way that best serves the needs of the downstream application of scheduling electricity supply. So this would be a predictive setting where, for example, our model would be taking in some historical data and outputting some kind of prediction. In reality, when we make that prediction, it's going to be used downstream to enable some kind of decision. So again, we predict electricity demand, and it's used to schedule electricity supply. And the hope is if we can write down the relationship between our prediction and the decision as an optimization problem, then we can somehow propagate this relationship between the prediction and decision back into the machine learning model so it can update how it's making predictions in the first place. So these are two examples of ways in which optimization in the loop machine learning can play out. So in the rest of this talk, having at a high level motivated optimization of the loop machine learning, I want to dive into some details. So first, I want to talk about the toolkit we actually use to do this, called differentiable optimization. And then dive further into the two settings I just talked about, the details of how do you actually create reinforcement learning methods that satisfy hard constraints as they're controlling a power grid or in another setting. And then also talk about how do you make forecasting models that are cognizant of how their predictions are going to be used. So first, this toolkit of differentiable optimization. So the motivation here is, while I've hopefully kind of, motivated why I think embedding optimization problems into machine learning models can be helpful, I haven't told you how we actually do this. All I've done is draw one box inside another box on a slide. And so what I'd love to do over the next minutes is talk about, how is it that we actually are doing this? How are we embedding optimization into machine learning methods? And we're specifically thinking about this in the context of deep learning. We're using a toolkit called differentiable optimization in deep learning. And so we and others proposed a general framework for this several years ago. So I'm going to talk about that. And then I'll also talk about some additional tools that exist today that are kind of easy to implement within your own work, sort of whether you're somebody developing the tools or not. So in order to do that, I'm going to give some background on deep learning, not because this audience isn't familiar with deep learning necessarily, but because I want to give my perspective on how deep learning works, as then a motivation for, what is it that we need to do in order to embed optimization problems within it. So this picture on the slide is the same representation of a machine learning model that I used before, where again, X are the inputs, H is the functional form of the model, theta are the model parameters, and H sub theta of X are the outputs. We also have a loss function on the slide that basically is a score for the quality of our output, where lower values are better. And we're using this information to adapt the parameters in our model iteratively, so that as we put more inputs through the model and we get more outputs and we compute more loss functions, that the performance on the loss function improves. So that's just machine learning more generally. But when we talk about deep learning, what we mean is that our machine learning model is a neural network. And a neural network is just a bunch of functions with parameters that are composed together. These functions tend to be nonlinear. That's what allows neural networks to be particularly expressive. But importantly, these are a bunch of functions with parameters that are composed together, where each of these functions is called a layer. The way we update these parameters is to minimize the loss function by basically putting information through the neural network, figuring out what the output is, computing a loss function on that output, and then computing gradients, basically saying what is the gradient of our loss function with respect to all of our parameters theta. And with those are computed via an algorithm called backpropagation. And once you compute those, you can use that gradient information to adjust each parameter in your neural network. The key implication of this is that if you put something into a neural network model or its loss function, if you put some function in there, you both have to be able to map between inputs and outputs. And you also have to be able to take derivatives through the function in order for this whole process of backpropagation and gradient descent to work. So basically, this means every single component, every single layer, and your loss function has to be differentiable. And as a result, if I'm telling you about this cool paradigm called optimization in the loop machine learning, where we're going to stick optimization problems into deep neural networks, I have to motivate to you, how is it that we actually make this work? How do we actually get this optimization layer in the neural network to be able to be differentiable? And I see there might be a question coming there. So let me pause and see if anybody has questions so far before I dive into the gory details here. All right, if no questions, I'll move. Oh, go ahead.
Yeah, I don't see a question, Priya.
Okay, if no questions, I'll move on, but please do feel free to jump in at any point. Yeah. All right. So the gory details here are basically, if we've solved our optimization problem and we can find a set of equality constraints or equality conditions that those solutions satisfy, we can just take derivatives through those conditions. And so for many optimization problems, for example, convex optimization problems, they have something called the KKT optimality conditions, which are, in the case of convex problems, necessary and sufficient to characterize optimal solutions. So the idea is basically, if we have a solution to our optimization problem and we plug it into the KKT optimality conditions, which it satisfies, we can just take derivatives through the KKT optimality conditions. So for example, there's this example optimization problem here. This is a convex quadratic program. We can then write down a selection of its KKT optimality conditions, which again are necessary and sufficient to characterize the optimal solutions of this problem. Once we've done that, we use the implicit function theorem, which basically allows us to take derivatives through these optimality conditions in the way that one would expect you could. And doing some, just some calculus here, you end up getting this system that looks something like this, where the middle term here are the gradients or derivatives that you're trying to compute. The left matrix here is the generalized Jacobian of our KKT conditions. And the right side are the gradients of our problem parameters. And basically, by solving this equation, you get the gradients that you need in order to differentiate through your optimization problem, or this is the result of differentiating through your optimization problem. Now, for those who are super familiar with the process of backpropagation and gradient descent, you might stop here and say, well, hey, in general, in neural networks, when you're doing backpropagation, you don't want to compute the gradients of the output of your layer with respect to the input. You want to directly compute the gradient of your loss function with respect to your input, because otherwise you end up with these really, really high dimensional matrices and tensors that you don't want to keep around in memory. And so we actually go one step further and use something called the Jacobian vector trick to rearrange these equations slightly and actually directly solve for the gradient of our loss function with respect to our parameters. But the details here for those who aren't completely in this area are not particularly important. The high level takeaway here is that for an optimization problem, if we've solved it, we do have the ability to take derivatives through it. And that's what enables us to actually embed it within our neural network. So, several of us first introduced this into the context of deep learning. So implicit differentiation has been around forever, but kind of bringing this into the context of deep learning to enable these kinds of optimization problems to be embedded as neural network layers. That work started with quadratic programs or pretty limited classes of optimization problems. And since then, there have been a lot of additional tools that have come out for combinatorial optimization, for power system optimization, for convex programming, for maximum satisfiability, for various kinds of optimization problems. And so basically, we now have this really powerful toolkit to embed optimization problems into deep learning methods. For those who have used the Python package CVXPy, any problem you specify in CVXPy, you can put it into another package called CVXPy layers, which spits out a neural network layer for you. So these tools have really gotten much more accessible. And so the question is, now that we have this really powerful toolkit to embed optimization methods into deep learning, how do we actually use it? And so I'm going to spend some time talking about two specific settings where we actually use this. So as I motivated earlier, one is reinforcement learning methods that satisfy hard constraints. And the other one is predictive methods that are cognizant of the downstream implications of their forecasts. But before I do that, I just want to pause and see if there are any questions on any of this so far.
Super clear.
Cool. All right. So onwards. All right. So the first setting I want to talk about is enforcing hard control constraints. So the motivation is on a power grid or in many other settings, you need a well-performing control method. It needs to kind of be, ingesting data about your system and really learning to do something very nuanced. But it also needs to guarantee the enforcement of hard constraints. Things like making sure to not black out your power grid. And so how do you do that? Our approach is basically to use reinforcement learning and say, can we take this approach of optimization in the loop machine learning to embed knowledge of hard constraints into the reinforcement learning techniques themselves? So I'm going to primarily dive into one setting, which is enforcing asymptotic stability in power grids. But I'm going to zoom back out afterwards just to emphasize that even though I'm going to get into the weeds of one particular setting, this idea of optimization in the loop reinforcement learning actually applies to a pretty broad range of settings where you have some kind of reinforcement learning algorithm that you want to use to construct a controller, but where that controller needs to satisfy some, physical feasibility characteristics or robustness conditions and so forth. You can use the sort of same method I'm about to talk about to do all of that. And so this work is positioned sort of in the middle of two different fields that try to think about controlling systems, one of which is deep reinforcement learning and the other of which is robust control. So deep reinforcement learning, coming from the machine learning side, basically says, let's take a machine learning model, like a deep learning model, and let's just throw it at a system and get it to propose actions that can be taken on that system. We're then actually going to take those actions. We're going to see how good they were by getting some kind of reward signal from our system. And then we're going to update our model on the basis of that to try to improve its performance. And this kind of approach has gotten, really, really good performance in various settings. So for example, achieving superhuman performance in games like Dota 2 online, that's deep reinforcement learning. Because the idea is that these algorithms are able to see a really large amount of data in a very large number of scenarios in order to then learn how to do something very nuanced and data-driven to perform well on average across those scenarios. The challenge, though, is that while they perform well in the average case, deep reinforcement learning methods are subject to fail and potentially catastrophically in certain situations. They don't have any guarantees on how they'll perform. It's just that on average, they are meant to perform well. In addition, you also need, access to a good simulator that has infinite samples about your environment, and you may not have that. So that's another challenge. And so there's often a need to, in particular, deal with that aspect, but also importantly, how do you make sure that you have a deep learning algorithm that isn't just going to catastrophically fail? On the other side of things is robust control. So in control theory, sort of this idea of guaranteeing stability and guaranteeing robustness is put at the center. And what control theorists do in order to do this is they'll write down some kind of uncertainty specification for their system to think about what are the things that could go wrong on the system. And then they'll kind of write down an optimization problem mathematically to then solve for a controller as well as a certificate, like a Lyapunov function is an example of a kind of certificate that will kind of show that their controller is indeed going to provably stabilize the system. The pro of this, the good thing about this, is that you get provable guarantees. You know how your controller is going to behave under worst case conditions. The challenge, though, is that the resultant controllers are relatively simple. You often have to make various simplifying assumptions, like assuming a linear functional form on your controller, for example, in order to actually solve for a controller with these attributes. And this means that when you're controlling a more complicated system, but you have a more simple controller, that you're leaving a lot of performance on the table. And so the question is, how do we bridge between these two worlds? How can we improve performance in the way that reinforcement learning algorithms do, while still guaranteeing stability in the way that control theoretic methods do? And so our approach is basically as follows. So we start with a neural network, and this neural network takes in information about the state of our system, and it outputs some proposal for an action. However, this is not the action we actually take. Instead, we project that action onto a set of actions that we've determined to be safe. And I'm going to kind of come back to how we actually find the set of actions. But we project that action onto a set of actions that we've determined to be safe. And then the output action is the one we actually take. Since this projection is an optimization problem, and I've just told you that we can kind of embed optimization problems into neural networks in a differentiable way, our model, this neural network plus projection, is a differentiable model. So we can train it sort of in the same way we would train any like reinforcement learning algorithm. We would get some kind of reward. We would compute gradients in order to update the underlying deep learning neural network. And the result is that we get a deep learning based neural network policy that has provable robustness guarantees. Provably we can say something about the output of this neural network, but that is still trainable using standard reinforcement learning approaches, which is to say you can train it in a data-driven manner so it's really able to adapt the nuances of the underlying system. Now, I've left out a big detail here, which is how do we actually compute this set of actions that is supposed to be magically helping our controller come up with a provably robust action. And the takeaway there is that we basically take a lot of machinery from control theory in order to construct that set of actions. Basically, if we're at a given state, we find a set of actions that are guaranteed to satisfy what are called Lyapunov stability criteria at that given state, even under worst case conditions in our underlying system. If we can find such a set of actions that are guaranteed to satisfy stability criteria and we project onto it, then the output is an action that will satisfy the relevant stability criteria.
Priya, can you say a little bit more about or maybe you're about to do that, what a Lyapunov stability criterion is?
Yes, I'm just about to. So great question. Awesome. So before I do that, I'm just going to do the setup a little bit. So basically from robust control, we take a couple of things. So first is an uncertainty model for our system. So we have a system with state X, action U that we specify, and an uncontrollable external disturbance W. And then the kind of time evolution of the system, so how this state changes over time, is contained in some set characterized by a function of our current state, our current action, and the uncontrollable disturbance. This disturbance term in particular can be arbitrarily nonlinear. It can be some weird nonlinear function of our state and our action. But we do have some knowledge of a bound that it might satisfy. So in this case, this is an example of a norm-bounded linear differential inclusion style bound, which basically says that the L2 norm of our disturbance term is bounded by this particular function of our state and our action. But basically, we have some dynamics. We don't fully know them, but we do have some kind of uncertainty specification on them. We also have a Lyapunov function. So a Lyapunov function, you can think of as a potential function for your system. So if you think about like, this is what the schematic here is. If I'm, at the top of a hill, I have a lot of potential energy and I can kind of go, to the bottom of the hill, and then I have, less or no potential energy because I've come to sort of a stable state. I've come to a ground level. A Lyapunov function is doing something similar. It's a function where it's a non-negative function. High values indicate that you are farther from a stable place, and values close to zero indicate that you are close to stable. And so the Lyapunov function, it might look like a quadratic function of your state, for example. We can obtain such a function using this robust control synthesis approach that I hinted at earlier, where in robust control, when you're actually obtaining a controller, you're writing down some kind of optimization problem that allows you to solve for your controller, and you're alongside that solving for a Lyapunov function that you can use to basically show, okay, my controller is appropriately, satisfying some condition on the Lyapunov function at every point in time. It's actually stabilizing the system. And the condition that one of the conditions that you can try to satisfy, this is the one that we use, is this exponential stability criterion, which basically says that the change in our Lyapunov function at any given moment in time has to be such that it decreases by at least this amount on the right side. Or sorry, it increases by this amount on the right side. There's a negative sign. It decreases by alpha v. Basically, all this condition is saying is, I have a Lyapunov function. It has some kind of positive value. I want to drive that value towards zero. And how I do that is by making the value decrease by at least a certain amount at every point in time. Lisa, does that answer your question about like the great? So given that, what we do is we say, all right, so we're at a given state. Can we find a set of actions that satisfy the exponential stability criterion for our Lyapunov function, even in the worst case? And the worst case basically means, remember, we have this uncontrollable disturbance on our system. If that disturbance behaves as badly as possible, we still need to make sure that our Lyapunov stability criterion was satisfied. And so we just do some algebra to figure out what that set of actions is. Basically, the left side of this exponential stability criterion ends up depending on the uncontrollable disturbance because you have the sort of time derivative of the state kind of in there. So you basically say, if we make what causes it, what actions still cause it to be less than or equal to the right side of the equation. And by doing that, we end up being able to solve for a set of actions, and it ends up being convex, and it also ends up being non-empty, which is important because that means that we can actually, like, there exists a projection onto it. We can actually project onto it and get some kind of value that is output. And so just to bring the picture back up, this is then the set of actions we put into this projection on this side. We have the neural network. Its output is projected onto this set of safe actions. So this is the set of actions that we now have that I just kind of described. So why go through all this trouble, right? Why go through all this trouble of kind of embedding this control theoretic criteria into our deep reinforcement learning workflow? And to show that, I want to kind of show some results on an illustrative system. So on the x-axis, we have different methods that we compared. So we have some non-robust methods, both from control theory and from reinforcement learning. We have a robust control method from control theory. I'm only showing one here, but in our paper, we have comparisons against others. And then we have our methods here, which combine control and reinforcement learning. And we're going to compare all of these methods in two settings. The first is an ordinary setting where we have our system trained on, our system is trained using some kind of simulator with some kind of disturbance on it. And during test time, we assume the disturbance has a similar distribution to what it had during training time. We also look at an adversarial setting where for each individual method, we construct a disturbance that is as bad as possible for that particular method, basically to try to get it to go as unstable as it can. This isn't necessarily a realistic setting, right? In many cases, the disturbances are sort of natural as opposed to explicitly adversarially constructed. But the goal is here, we're just trying to stress test the methods, basically see how they behave kind of in the best case versus how they compare in the worst case. And so there are a couple of things I want to point out on this slide. The first is when you compare the average case performance of our methods with a traditional robust control method, the performance improves quite a lot. The y-axis here is on a log scale. So you can see like basically an order of magnitude improvement between using our method versus using the kind of standard robust control method. Some of the non-robust methods, though, are way better. Like particularly this model-based planner, it has even an order of magnitude less LQR cost than our methods. But if you look at those non-robust methods in the adversarial case, all of the non-robust methods go unstable. The moment you apply kind of a worst case disturbance to them, they overflow basically like the capacity of the float that is representing the LQR cost, they go unstable. Whereas in the kind of adversarial case, all of the robust methods, both ours and the control theoretic ones, stay stable. And so this is the key kind of trade-off that we're trying to sit in the middle of. We want to improve performance in the average case compared to robust control methods, but we also want to stay stable even in the we also want to stay stable even in the kind of adversarial worst case, which is something that the non-robust methods aren't able to do. Now, at the moment, this does not come entirely for free, unfortunately. The downside is that there is some more computational cost to our methods. This is because every time we run our reinforcement learning controller, we are having to solve a projection onto a convex set. And while that projection is fast compared to other optimization problems we could be solving, it is slower than it is an order of magnitude slower than some of the other operations that we're doing when we usually kind of resolve passing information through a neural network or passing information through our LQR controller. So this is definitely an area of future work and one that is important to work on. So before I wrap up this section of the talk, I did want to zoom back out and say I did go very deep into the weeds in the sort of specific kinds of stability that we're trying to satisfy in a particular setting. But I wanted to zoom back out and say, again, this idea of embedding optimization-based projections into neural networks extends beyond just that setting and in general can be used in a wide variety of settings where you have some kind of physical constraint that you need a reinforcement learning controller to satisfy. For example, we use the same kind of thinking to control the heating and cooling system in a simulation of a building at Carnegie Mellon, where the goal is to control the supply water temperature to a heating and cooling system in order to minimize energy use, while also respecting constraints of the underlying equipment and maintaining the comfort of the building. And the method we use here is very similar. We have a neural network. We have the neural network propose an action. We project that action differentiably onto a set of feasible actions. And then the output action is one that satisfies the constraints we need to satisfy. So we can just train this whole model end to end. And the key detail that changes from setting to setting is this idea that, how do you actually get this set of good actions? This is where you need some, domain knowledge about what the requirements of your underlying system are, and is a great opportunity to basically incorporate often the years and years of sort of control theory and optimization and physics knowledge and such that have been developed in these areas, and kind of, actually incorporate it into the design of a reinforcement learning based controller. And yeah, I mean, there are some results here on the realistic scale building controller as well. We end up finding that we're able to, improve energy efficiency with respect to other methods by something like 4 to 24%, while still maintaining our constraint of thermal comfort. So basically this idea that by embedding the domain knowledge and embedding the constraints into our method, It's able to kind of learn in a constrained cognizant way. So it's able to learn how to improve energy efficiency, knowing how its output is going to be modified to satisfy equipment constraints. And then it does ultimately satisfy those constraints as well. So to summarize this part of the talk, the basic idea is, again, we need well-performing control methods that also guarantee the enforcement of hard constraints. And the key insight into how we do this is that we can write down a set of safe actions using domain knowledge, and we can project the outputs of the neural network onto this set of safe actions. If we can do this projection in a differentiable way using an optimization layer, we can train the whole thing end to end in a way that allows the neural network to actually be cognizant of how its outputs are being projected. And this tends to improve overall performance and sort of allow the neural network, again, to actually take this into account. There are lots of interesting future directions here. So this is just one example of ways in which to bridge reinforcement learning and robust control, but just in general, I think this area is very fruitful to be in. And then improving computational costs, as I emphasized earlier, making sure that we can kind of use this domain knowledge within the neural network, but that we can do so in a way that is not so expensive as computing fully an expensive optimization problem every time. So that wraps up the portion of the talk focused on, hard control constraints. And I again would like to pause and see if anybody has any, questions or comments or anything like that that they'd like to weigh in with.
Yeah, a question: how? What are the restrictions on the sizes of the optimizations that you can do? Any numbers of variables? Can you do non-convex cases? How broad can you go here? You showed
Great question.
Quadratic optimization with a fairly standard one, very important, but maybe not everything we want to do.
Yeah. So what I'd say is that in terms of size, you can support fairly large optimization problems. In some sense, it's sort of your intuition about what optimization problems can we solve in general, and what are their runtimes, and what is their computational complexity that fully generalizes over to this setting. A lot of the work in this setting, when it comes to then making those optimization problems differentiable, tries to basically figure out how do we get the derivative for free based on the computations we already did to solve the optimization problem in the first place. So for example, in the quadratic programming setting I showed earlier, you have to invert a particular Jacobian in order to get your gradients. And that kind of inversion of the Jacobian is the most expensive step. But it happens to be a Jacobian we already would have inverted when solving the optimization problem in the first place. So we can just use that. So a lot of the work in differentiable optimization basically tries to get at this idea of, can we make it so having a differentiable optimization layer is just no more expensive than actually solving the optimization problem in the first place? And so all the intuition about the size of that and what can be supported in optimization solving generalizes. In terms of non-convexity, so the KKT conditions approach I showed earlier would not work for a non-convex problem, in the sense that, or at least it would not be the most principled thing to do for a non-convex problem, because it's, KKT conditions are not necessarily, necessary and sufficient for optimal solutions for non-convex problems. And so people deal with this in all sorts of ways. They'll use relaxation. They'll find some fixed point conditions that they know don't always, in sort of the most principled optimization way, give you a good gradient, but most of the time give you something that looks like a gradient. And so you can do it that way. And so, and approaches like that, basically, in the optimization realm, can you take a non-convex problem, kind of come up with a convex surrogate, and are you happy enough with the resulted gradient? Or can you leverage stuff like the KKT conditions and fixed point equations anyway, even though you technically shouldn't do that, and have that sort of come out okay anyway? Yeah, I see a question from Saad.
Yes, I actually have a question. So it works for worst case scenarios. It can actually be relaxed for like value at risk constraint, and if I'm actually thinking for an application of the 27 carbon-free energy, where like can actually be applied for some kind of problems that you want to actually satisfy, say, a 90% clean energy procurement with some objective function that could be like a cost or quadratic case.
Good question. Is that a setting where you would use like a reinforcement learning algorithm, or where you would traditionally just specify kind of like an optimization problem you can solve for procurement?
So initially it would be an optimization problem, but I would actually also think that reinforcement for because eventually you'll have an online decision making in which you want to buy, for example, some clean energy from somewhere, but then it will not necessarily be sufficient. So you'd get energy from a power grid or something similar to that. So you need to make those kind of specifications.
No, that totally makes sense. And yeah, I mean, there are kind of other constrained reinforcement learning frameworks that are potentially useful in that setting. So like constrained Markov decision processes that basically say you have some kind of budget for constraint violation. So where that budget might be like procurement of non-clean energy over a particular time horizon. And then you try to figure out how to construct your reinforcement learning algorithm to deal with that. Or if you have an algorithm where your action is itself sort of like a multi-horizon decision, then you could sort of project that multi-step decision into a constraint that like constrains that overall set of decisions to be under your budget, and then you could do it that way. Here we definitely are looking at settings where at every point in time, like for whatever your output is of the reinforcement learning model, for every point in time, you have an instantaneous constraint that you can make sure to satisfy. So even the Lyapunov stability one, we're trying to specify something about how our system behaves over time, but we have a constraint. That whole like exponential stability criterion was about coming up with a constraint where you can instantaneously project your action now, but you know that that's sort of helping you work towards converging. You sort of need to be able to specify like what is the what is the set that my current action should be constrained to. Otherwise, if you're more about, okay, it's fine if it violates the budget a little bit now, but we couldn't violate the budget a bit later, then maybe something more like a CMDP approach might be more appropriate.
Priya, there's another question came over chat.
Oh, yeah.
And because of the insistence on differentiable steps, does that mean you can't have discrete controls?
That's a great question. So not necessarily. So you could definitely, for example, do something like, okay, well, there's two answers to that question. So one is you can do things like have your output be kind of a quantity that is then rounded later on to a discrete quantity. The other thing is there again is some work that's trying to embed discrete optimization or mixed integer optimization, for example, into neural networks. And though much of that is, again, depending on this idea of like soft relaxing stuff and then rounding it post hoc. So definitely kind of continuous things play the most nicely with the machinery we have in neural networks, but you can kind of make discrete stuff work with a little bit of massaging.
Great, thanks.
Yeah. So any other questions on this part before I move on to the last? Okay. So having talked about the setting of, provably robust reinforcement learning using optimization in the loop machine learning, I want to talk about a different use of optimization in the loop machine learning in the prediction setting. So the motivation is we are making predictions all the time. So for example, on a power grid, you might predict what is my solar power output going to be, or what is my electricity demand going to be. And these predictions don't exist in a vacuum. They are almost always used to make some kind of decision. For example, given knowledge of what my electricity demand will look like, how do I schedule electricity supply? And yet, even though one might argue that's the actual objective we care about, the quality of our downstream decision, that's not what we tend to optimize our predictive models for. We tend to optimize them for accuracy. And if you have a perfect predictive model, that's great. But since you don't always have a perfect predictive model, you want your model to make appropriate trade-offs in how it's making errors so that it doesn't make errors that are particularly bad for the decision maker. And so we take this approach of constructing decision cognizant or task-based models via optimization of the loop machine learning in order to enable this. And so I'm going to start by talking about a first setting of decision cognizant electricity demand forecasting. And then I'll sort of talk about two other settings where we can apply similar thinking. So the decision cognizant demand forecasting approach we're looking at is in the following setting. We're trying to predict at the beginning of a day electricity demand for the next 24 hours on an hourly basis with uncertainty, with error bars. We're doing that by taking in information about past electricity demand, past weather, and so forth. And we're trying to construct a machine learning model that can map between these two quantities. Usually what your machine learning model would do is try to minimize the notion of distance between your predicted quantities and your actual quantities. So for example, H sub theta of X is our predicted demand, Y is our true demand, and you try to minimize some loss function like in a deterministic case, something like root mean squared error or something like log likelihood in a probabilistic case to try to minimize the error of your prediction. But as I started to motivate, our prediction doesn't live in a vacuum. When we make a prediction, it is used to make some kind of schedule, like of electricity generation. And that electricity generation schedule is then enacted on our real system. And we want to understand how that electricity generation schedule performs when it's enacted on our system. So instead, that potentially implies a slightly different objective here. I'm going to let Z star X theta refer to the best decision the decision maker can make if they assume that our prediction is true. So the reason for the notation is our prediction is made by taking in some data X for current parameters of the model theta. That causes us to make a prediction, and that causes the decision maker to make a decision. So this is the best possible decision the decision maker can make, assuming that our prediction is correct. We then want to understand how good is that decision when it acts on the true electricity demand that actually results on the system. And so that's what this cost function is saying. It's basically saying, what is the quality of the decision that is implied by our prediction? And this is actually what we're going to optimize our forecasting model for. So putting that pictorially, this is our model looks like this. So we have a neural network. It's taking in some data. It's predicting some demand. We put that predicted demand through a power system optimization model. And that power system optimization model spits out a power generation schedule. We then kind of assess the quality of that power generation schedule when it acts on the true electricity demand. And since this power system optimization model is an optimization model, which I told you we can differentiate through, it satisfies this condition that our loss function is differentiable. So we can kind of backpropagate through this loss function to update the parameters of the neural network, and as a result, come up with this decision cognizant model. So again, why go through all this trouble to come up with this decision cognizant approach? It turns out that when you look at the quality of the decisions that result when using a prediction made by this kind of model, the quality of the decisions increases significantly. And so to show this, I'm going to show two plots. The first plot compares our model, which is the green solid line, against a standard neural network model that is just optimizing for accuracy. That's the red dashed line. We're going to compare both of these models on the basis of accuracy on the y-axis for each hour of the day, since they're making predictions hourly over the course of the hour or day. On this plot, what you can see is that our method is doing worse. It is making predictions that are slightly less accurate than the model that is optimizing for accuracy. Maybe unsurprising. The accuracy optimizing model wins when it's optimizing for accuracy. But when you look at the implications of those two models for the quality of the decision, so here we have decision cost, if this is a quantity we want to lower, we see that the picture reverses. And taking this decision cognizant approach improves our decision cost by almost 40% when enacted on the system. The reason for this might not be fully obvious. I've given this sort of abstract motivation for, you want to make sure that your errors are not bad for your decision maker, but let me try to make this concrete. So if I predict electricity demand and I overpredict electricity demand, that's kind of bad for my decision maker. They end up scheduling more power than they need. And that incurs unneeded costs, unneeded emissions, and so forth. If I underpredict electricity demand, that causes me as the decision maker to potentially underschedule electricity generation. And if I have to make that up, buying additional electricity generation on the real-time market and scrambling for that is potentially very costly. And if you can't do it, it potentially blacks out the system. So the implications of overpredicting demand versus underpredicting demand are different for the decision maker. But when you're just optimizing a model for accuracy, it doesn't understand that underprediction and overprediction are different things. And so it can't account for them. And so that's a simple example. There are also some time dependencies where, for example, our system has ramp rates where if you get a power generator to generate a certain amount of power right now, and you need it to generate a lot more power later, it can't necessarily like ramp up its power generation in time. So there's some dependencies among different time steps. But the basic idea is that some mistakes are worse than others. They have even two predictions that might feel similarly accurate have completely different implications for the downstream decision. And so what's happening here is that our model is making some trade-offs in terms of, okay, maybe I'll be slightly less accurate here, but in a way that causes my decision maker to act in a better way than if my prediction had been kind of, throwing them off.
So, Priya, is this, would it be fair to say that what your technology allows is to make more discerning loss functions that are feeding back into your model training that allow it to do more what people want as opposed to more coarse loss functions?
Exactly. And so in this case, it's exactly what's happening. It's you're able to specify better loss functions because you have additional toolkits with which to do that in order to then, enable the prediction to do what you'd like. In the kind of control setting, the optimization problem is embedded not in the loss function, but in the model. So it's about making sure that the model is constrained in a way such that you can say something provable about its output. But in all cases, it's exactly this idea that now that we can specify more complicated things within our loss functions and our models, we can embed more of the requirements and desired performance characteristics and knowledge of that into the way we design them.
Great, thank you.
Yeah, thanks. All right, so I gave this example of a model that's cognizant of the downstream implications of its prediction. And we've used that same kind of thinking in several other contexts. So for example, there's this power system optimization problem called AC optimal power flow that needs to be solved more accurately and more quickly in order to optimize power grids with large amounts of renewables. And so the problem looks something like this. It has power demand as an input. It outputs power generation schedules, trying to minimize cost subject to physics. And we provide fast approximations to this optimization problem that try to improve performance and also satisfy various constraints by basically using a neural network to map between the same inputs and outputs as the optimization problem, and stick knowledge of our physical constraints, of our costs, of all of the other things in the optimization problem into a combination of the neural network architecture and the loss function. So exactly, again, as Lisa mentioned, this idea of you have requirements that the output of your neural network needs to be physically feasible on your system. You want it to minimize certain costs that your optimization problem would have optimized for. Using this paradigm of differentiable optimization, you can do that. And we end up seeing on a kind of small power systems test case that we're able to come up with high quality solutions, which is to say like pretty good objective value compared to a traditional solver. But we're able to reduce solution times by a factor of 10 to do that. So it's pretty cool. And then we use a similar kind of thinking to address a robust optimization problem in power grids called N-K security constrained optimal power flow. This is a problem where you have to be scheduling power to be robust to potentially K things failing at the same time. So think about like the Texas power outage where, because it was cold, lots of different things failed in lots of different ways at the same time. How do you schedule a system that can adapt to and is robust to that? And this problem is increasingly important to solve, but if you want to deal with all combinations of K failures that you could see on your system, you're dealing with billions of scenarios. It's a very large problem. So we end up kind of reformulating this as a bi-level optimization problem, and using some of these same kinds of techniques from differentiable optimization combined with another toolkit called adversarial robustness to deal with this. And we end up seeing that, yeah, this kind of embedding differentiable optimization and adversarial robustness to kind of heuristically solve this problem allows us to basically speed up how long it takes to solve this problem sufficiently fast for real-time operation on a realistic scale system, while kind of reducing the number of times that our system sees a failure that it's not able to deal with. So the summary here basically is that, yeah, you have some kind of predictive methods that operate within some larger decision-making or physical process. And we want to just make sure that predictive model takes this into account. And the idea is that we can incorporate knowledge of this downstream decision-making or physics process in the loss function using differentiable optimization. In terms of future direction, so all of the decision-making paradigms I've talked about today are ones where you can write them down in a very clean mathematical format and differentiate through them. And that needs to accommodate a wider range of decision-making paradigms because some of them are mathematical, but just harder to differentiate through for various reasons. And some of them are non-mathematical. You often have predictive processes where someone is manually making a decision on the other side. And so while there's maybe legitimate philosophical debate about whether a human can be characterized as an optimization problem, I'm not going to get into that here. But the idea is that we have, a wider range of decision-making paradigms that we need to take into account. And then in addition, while I've made this whole case for why it's really useful and important to have these decision cognizant and task-based models, it's also the case that sometimes when you make a predictive model, you use it in multiple places. And so I think having a better formal understanding of what tasks is our model better tuned to and what tasks are not similar enough to that task where you'd have to retune the model or where you wouldn't want to use the tuned model for a different task. I think that also becomes important to understand. So to wrap up, today I talked about optimization of loop machine learning, which is a framework for embedding physics hard constraints decision-making into machine learning models, and specifically in the context of deep learning. And I talked about two settings in which this can play out. One of them is enforcing hard control constraints in reinforcement learning, and the other of which is incorporating downstream decision-making considerations into predictive models. I am excited to talk further both now and sort of in further communication. So here's my email address on the slide. But before I wrap up, I just also want to mention, so I'm here in my capacity as an assistant professor at MIT. But the slice of work that I talked about today is sort of one representation of where machine learning is being used for climate action. And for those of you who are more broadly interested in this space, I would encourage you to also plug into the Climate Change AI network. Climate Change AI, it's a nonprofit that empowers this global community to come together to do impactful work at the intersection of climate change and AI broadly. And we do this by trying to provide, education, opportunities to share work through workshops and online events. We have grant funding available, and we also try to provide research on kind of the broader opportunities, bottlenecks, and needs in the space. So a bunch of different sort of resources available online in terms of kind of reports to read, workshops that you can submit to. We currently have a call for submissions open for our workshop at NeurIPS in December. And then we also provide grant funding, we have webinars, we have a community platform and so forth. So I would definitely encourage you to check out the network and plug in if it is helpful to you. And yeah, with that, that's what I had prepared. And so I'm looking forward to any further discussion and questions.
Well, let's start by thanking our speaker. That was absolutely awesome. Beautiful mix of seeing the forest and the trees, something we don't get very often. So thank you for that really beautiful presentation. I'd like to open it up and encourage others to ask questions if they haven't already. I've had quite a few. Well, if there's nobody, I will ask a question. Can you put that slide back about this organization? Can you say a little bit more about it? Who's in it? How did it start? And in just a couple of words, what is it trying to achieve?
Yeah, sure. So Climate Change AI was co-founded 4 years ago by myself and a bunch of, at the time, other graduate students and postdocs, coming both from climate change related backgrounds and machine learning backgrounds. Basically a mix of people in machine learning who are thinking, I have these skills in machine learning, how do I find, if I want to kind of leverage them for climate action, how do I find the most impactful problems? How do I build interdisciplinary collaborations? And how do I get the resources I need to both, direct and conduct this work? And similarly, climate change related researchers and practitioners who are starting to face various bottlenecks in doing their work and wanted to sort of either learn more about machine learning themselves or be connected with collaborators who could bring that together. So that's how the organization started. Basically, a group of us who came together, we wrote that paper called Tackling Climate Change with Machine Learning that I mentioned at the beginning to try to basically just lay out what is this space of AI applied to climate and how do you, what problems are in this space, what are some considerations for navigating it. And we launched it alongside a workshop at one of the main machine learning conferences, ICML, and it just sort of snowballed from there. And so really the objectives of the organization are to democratize and spread expertise at the intersection of AI and climate. So making sure that people from more domains and more geographies and more contexts have access to the kinds of information that are needed to implement AI for climate action, both impactfully and responsibly. So also thinking about what are the ethical considerations, what are the considerations in terms of who holds power in society, all of that. So in addition to democratizing information, then we also try to bring together people in more explicit collaboration and teams in order to then kind of scope and execute on work in the area. And so, yeah, so like in terms of who is involved, it's basically kind of anybody who's a kind of a researcher, a practitioner, or a decision maker who thinks about some aspect of AI or climate and has an interest in bringing those together. And in terms of ways to plug in, basically, if for example, in this room, we have various folks in the research community, you can submit to our workshops. And we also run like special issues of special tracks of journals like environmental data science that are focused more explicitly on this. We also have a summer school that provides kind of lectures and tutorials on this topic, and also brings together people for cohort-based, team building. And again, sort of grants programs that we run, webinar series. So just various ways to kind of find out what other people are doing, learn more yourself, and find collaborators to do things with together.
Great. Well, thank you for that. I just want to mention something that we've been quite focused on here that you didn't say, which is there's this question of deploying capital, how
Yeah.
working to get money to new technologies that make us all greener and stuff like that. And this is an area, I don't know how much you focused on it here, but perhaps might be grounds for a further conversation that we could have. Certainly a lot of machine learning in that specific type of application. So I will
Absolutely.
follow up on that.
Sounds great.
If there are no more questions, I will thank you again for an absolutely beautiful talk, and mention to the group this time next week, we will also be having a virtual talk. And our speaker is Emmanuel Platankis from University of Bath, who will another machine learning talk. That seems to be the flavor of this part of the seminar, when Bayes Stein meets machine learning. So I hope to see many of you then. Wish everyone a great day. And thanks, Priya. It was great.
Thanks so much, everyone. Bye.
Thanks. Bye.